In the meantime, let's continue with product rule. A very classical problem here. We have f of x equals the square root of x times g of x. Well, where g of x is just some function, actually they're not telling us whether it's a polynomial, whether it's another radical maybe, or a power function, or an exponential function. Well, we don't know. So we're going to find the derivative of this function using the product rule. And the reason for which we use the product rule is because we have a product of the function, the product of square root of x times the product times g of x. But in this case, they're asking us to evaluate the derivative at 4. In other words, the value of the slope at 4. But they're giving us information for g. When g is evaluated at 4, the result is 2, and when g is the derivative g prime is evaluated at 4, the result equals to 3. So in this case, we really don't need to know what g of x is, because they're giving us values for both the function itself and its derivative. However, well, let's just treat this as another function. But number one, how about we recall what the product rule for differentiation is? So in this case, when we differentiate, in this case, because we already have this f, let me use this in terms of u and v. So this prime means differentiation. So when we differentiate a product, what we do is differentiate the u, which is the first factor, times the v without doing anything to it, just as is, plus the derivative of v, the second factor, times the u function itself. Alright, how is that going to work for this given function? Number one, so we have a radical function as one of the factors. We cannot differentiate the radical just like this. So what we're going to do first is rewrite the function f of x. We're not going to write f prime, and we're going to write this square root of x as x to the 1/2 times g of x. Only then we will be able to find the derivative of this function. So f prime of x will be using the product rule, that is the derivative of the first factor. So actually I'm going to denote this to make our lives easier for a second. So that's the derivative of x to the 1/2 times g of x, that is the derivative of the first factor times the second, plus g prime of x, which is the derivative of the second factor, times x to the 1/2. So really all we have to do is differentiate the x to the 1/2, and we may go about the general power rule. Well, the general power rule to differentiate is, well, let me write it down here, d dx of x to the n, that's n x to the n minus 1. In other words, all we have to do here is multiply by the old exponent and subtract 1 from the exponent, and that's going to give us the derivative. So what do we have? A 1/2. 1/2 minus 1. Well, first of all, this is 1/2 times x to the 1/2 minus 1. Isn't that negative 1/2? And times g of x plus g prime of x, which is just g prime of x, times x to the 1/2. But how about, well, let me leave it as x to the 1/2. And well, so we have the derivative. We are just done with the calculus part of the problem. The remaining part is just algebra. Number one, rewriting these negative exponents in a nicer form, into positive form, and then writing those rational exponents into radicals, which are easier to handle rather than these weird looking numbers. So f prime will be, so number one, 1/2 x to the 1/2 times g of x plus g prime of x times x to the 1/2, which I'm just going to go back to radical notation. And then I'm going to do the same with the denominator of the first term. That is 1 over 2 root of x times g of x plus g prime of x times the square root of x. So that's the derivative simplified to nicer terms. Now they're asking us to evaluate this derivative at 4. So we're going to do the following. We will evaluate the derivative at 4, f prime at 4, that is 1 over 2 root of 4 times g evaluated at 4 plus g prime evaluated at 4 times the square root of 4. And well, here is where we use the information that we're given, that g of 4, whoops, I meant to highlight this, g of 4 equals to 2 and g prime of 4 equals to 3. So ultimately this becomes a 2 and this becomes a 3. Let's just simplify this. So number 1, in the denominator we have a 2 times square root of 4. So square root of 4, which is 2, times 2, that's 1/4, times the 2 that replaces the g of 4, plus 3 times the square root of 4, which is 2. Well, what do we get here? 2 over 4. Isn't that 1/2 plus 6? And well, what about 6 over 1? 2 and 2. That's 13/2. So that's the slope for this function when x equals to 2. And that's a very classical problem whenever most likely a problem you'll see on the exam in which you have to do the product rule or even the quotient rule, but one of the factors is not a known function. It's just some g of x, some generic function. But in this case, you will be given additional information such as the value of that function at the given value and the value of the function at its derivative. Yes?
I know this is really far out, but when do you think the next midterm date will be?
I believe it's usually like 4 weeks between midterms.
Okay.
So that to allow, because it's 16 weeks, so it's 4 weeks midterm, 4 weeks, and then the last 4 weeks or 3, and then the final.
Okay.
Right? So let's see. So let's move on to the quotient rule. And again, so let's start by looking at the fact. So what if we have this quotient? Well, is q prime of x equal the derivative with respect x of x to the 6 divided by the derivative with respect x of x cubed. So this would be 6x to the 5th over what's this? 3x squared. So this reduces to 6 over 3, that's a 2, and x to the 5th divided by x squared, isn't that an x cubed? Well, that's one of the potential results. But in this case, well, is the quotient rule really the quotient of the derivatives? In the same way that we did for the product rule to be the product of the derivatives? Well, how about we do the algebra first? So q of x equals x to the 6 over x cubed. That's actually x cubed. Now, take the derivative. Oh, check this out, 3x squared. Do these two answers actually match? So there must be something wrong with one of them. And in fact, well, I'm just going to say that in this case it's not just going to be the quotient of the derivatives. So we're going to scrap this one. Alright? Instead we have to use the quotient rule. And no, that quotient rule, I'm not going to derive it in terms of f of x plus h the same way we did it last time with the product rule. So I could leave that for you as an example instead. I mean, as an exercise. Instead, we're just going to use the formula for the quotient rule, which in a more compact way, whenever we differentiate a quotient u over v, so u prime v, v prime u, where have we seen this u prime v, v prime u? Isn't that in the product rule as well? However, the product rule had a plus in between. The quotient rule has a negative in between, and everything is divided by the denominator quantity squared. So that's the quotient rule in contrast with the product rule, which I'm going to write. So u times v, okay, u prime v plus v prime u. Alright, that's the product rule next to the quotient rule. See what they have in common, see the differences as well. Alright, so the u prime v, v prime u order, it's the same, but in this case for the quotient rule, it's going to be a minus, and everything is going to be divided by the denominator squared. So coming back to the question where the derivative of a quotient is that just the derivative of the quotient of the derivative? No, the answer is no. It's a little bit more than just that. All right. So, and well, notice that for the product rule, so the product rule very common. So very often times you may see it in different order: v prime u plus u prime v. But in this case, for the product rule, it doesn't matter, because we're adding the terms. So you can add 2 plus 3 and 3 plus 2, you can still get the same result. However, that's not the same for the difference in which this quotient rule is being involved. It involves finding a difference, and it's going to make a, no pun intended, but it's going to make a big difference here. Alright? Okay, so let's have a look at one example. Find the derivative of f of x equals x squared plus x plus 6 divided by x cubed plus 6. Oh, it should be as easy as doing 2x plus 1 over 3x squared. No, unfortunately, that's not going to be the case. All right. So, in the same way that I went about the product rule, so let's define the u to be the numerator x squared plus x minus 2, and v the denominator x cubed plus 6. How about we find u prime? Okay, that's the derivative of the numerator, which is 2x plus 1. Using the general power rule, no more limit definitions, no more painful process to find a derivative. Just go with the general power rule, and v prime to be 3x squared, and the derivative of 6. What's the derivative of a number again? 0. All right. So we got the 4 parts that we need to set up our quotient rule. Let me write that quotient rule again to avoid just scrolling up and down. U over v prime, that's u prime v minus v prime u. All divided by v squared. Alright. And well, so finding the derivative for this function, that's f prime of x. The u prime, what's the u prime in this case? The 2x plus 1 times v, which in this case is the x cubed plus 6. Alright? We got this first part in the numerator, and then careful, recall that this is minus v prime, which is, oh, I forgot the prime symbol here. V prime, which is 3x squared, times, u, which is itself x squared plus x minus 2. And then the whole thing has to be divided by the denominator squared. And in this case, the denominator squared is x cubed plus 6, just square this quantity. Okay. Let me do some labels here, just so you can see what are we doing here. So, this is u prime v, that's the u prime v, minus v prime u, v prime u. And all this in the denominator is the denominator v squared. Alright? Again, order matters in the numerator because we are differentiating two terms. Alright, so let's see if we can simplify anything. Well, in this case, we will have to do some foiling and simplifying. So, okay, so yes, it's gonna take a good minute to go here. So 2x times x cubed and 2x times 6. This will be 2x to the fourth plus 12x. And then on the next distribution, 1 times x cubed and 1 times 6. That's just x cubed plus 6. And well, I'm going to do the minus. I'm going to keep the minus for a second. And I'm just going to open parentheses and write down whatever we get from distributing the 3x squared over each individual term in the trinomial represented by u in this case. Alright? So, we're going to distribute 3x squared times x squared, 3x squared times x, and 3x squared times negative 2. So, 3x squared times x squared, that's 3x to the fourth. And 3x squared times x, negative 3x cubed, and 3x times negative 2, negative 6x squared. The whole thing still divided by x cubed plus 6 quantity squared. Don't forget to square the denominator. That's one very common mistake, to forget about squaring the denominator. Alright, so what are we going to have here? So let's see if we can reduce any like terms. So, okay, do we have powers? We have powers of 4. So we have a 2 minus 3. What is that going to be? Negative 1. Alright, so negative x to the fourth. Okay, what about cubics? X cubed minus negative, careful, minus negative 3x cubed. So that's actually adding a plus, right? So plus 3x cubed plus 1 more, 4x cubed. Right?
Why though? If x cubed minus 3x cubed.
Yeah, but this is positive x cubed, and this one negative times a negative becomes a positive. That's 3 plus 1 more becomes a 4. And then what else do we have? We have this quantity squared, but we don't have any other quantity squared to combine it with. Question? Plus 3x cubed. Oh yes, that's true. So that's a plus, and then that becomes so minus 2, right? So okay, thank you. And well, we don't have any other squares, so negative 6, that's a plus 6x squared, and plus 12x plus 6 divided by plus 6 quantity squared, and I would call it a final answer over here. No, because what are we going to have? A quartic polynomial? I mean, you could go further, use the rational root theorem that you learned back in pre-calculus, but it's not required. So ultimately on the exam, on the quiz, you will be tested on whether you can use the quotient rule and the product rule correctly. You're not going to be asked to simplify or to factor that crazy polynomial, which just looking at it, I think it's going to take me 20 minutes to fact, if possible. I mean, because sometimes you get crazy results about this one. So
when do we know from the exam when to simplify more or stop?
if you're given like a very complicated function, sometimes they're just going to tell you do not simplify, just show the quotient rule or product rule, and in parentheses do not simplify. And that's very typical on quizzes and exams due to the time sometimes it's given for those. All right, let's look at another example. Find the equation of the tangent line to the curve y equals e to the x divided by 1 plus x squared. So we're gonna do things in one single shot. Number one, find the derivative using the quotient rule, and then use all this information to find the equation of a tangent line. Well, we want the equation of a line. So to get the equation of the line, what are the two pieces of information required? What do we need? The slope and what else? Well, the y-intercept. Well, in general, just any point. All right. Well, we can get the point. That's what I'm going to do first by evaluating f of 1. That's e to the first power divided by 1 plus 1 squared. That's e over 2. Right. So that's going to be the point 1 e over 2. So that's the number one piece of information. And the next piece of information is the slope. And no, we're not going to do rise over run. We're not going to do y2 minus y1 over x2 minus x1. That's only the approximation. That's going to give us actually the average slope, the slope of the secant. And for that, we would need two different values of x. And we only have one single value of x. So, in this case, because we want the slope at a natural point, we will have to use the derivative. And in fact, we're going to use the quotient rule. And again, I'm going to write it down again. The derivative of the quotient u over v, that's u prime v minus v prime u, divided by the denominator squared.
That's the quotient rule?
That's the quotient rule because we have a quotient of two functions. And again, let's do one thing at a time. How about we do u equals to e to the x, v equals 1 plus x squared, and then u prime will be what's the derivative of e to the x? Itself, e to the x. And what's the derivative of 1 plus x squared? 2x. So we got everything we need to set up our derivative via the quotient rule. So f prime, or rather y prime, that's u prime, which is e to the x, times v, which is 1 plus x squared, minus v prime, which is 2x, times u, which is e to the x. Right? And then the whole thing divided by the denominator squared, v squared in this case, 1 plus x squared, quantity squared. Alright? Yes, so yeah, that's the thing. So there's not much to simplify over here other than factoring out the exponential factor. So that's e to the x, multiplying, okay, 1 plus x squared minus 2x, but instead I'm going to write it in descending order of powers just to make it look nice. So x squared minus 2x plus 1 divided by 1 plus x squared. And in fact, this would be the final answer if we were just finding the derivative. There's really nothing else to do, simplifying, really. Well,
What would be for the first part though? You wouldn't be able to cross out 1 plus x squared. Denominator? No.
Yeah, but it would have been like e to the x over 1 plus x squared minus 2x e to the x over 1 plus x squared. Well, we would still get like two terms, and well, we prefer to get everything into one single term. This wouldn't be an incorrect answer. If you put that on the exam, that should be acceptable. All right. But because in this case we want to use the derivative of the function, to find the slope, it would be better to have it in the most simplified version, so we don't have to deal with too many quantities. That is, we're going to do the evaluation y prime. This bar right here, this vertical bar, means evaluated at x equals to 1. And what we're going to do is plug in 1 wherever you see this this letter x. So e to the first times 1 squared minus 2 times 1 plus 1 divided by 1 plus 1 squared, quantity squared. And in this case, let me just do the 1 e to the first, 1 squared, 2 times 1, another 1 squared. And ultimately, I'm highlighting what we're plugging in for x. Alright, so let's simplify this to get the derivative. So 1 squared minus 2, that's negative 1 plus 1, 0. It doesn't matter what you multiply that by and divide by what. As long as the denominator is not a 0, that's e times 0 over, what's this, 2 squared, that's simply 0. Alright, so what else do we have? So now that initially we got the point, now we have the slope of 0, and we're going to use this information to get the equation of the line using the point slope form of the equation of a line. And the point slope form, it's simply, well, we have used that a few times already, y minus y1 equals m times x minus x1, where m is the value of the slope, which we just found to be 0, and x minus x1, that's 1, and y minus y1, that's the value of y in the given point. But check this out, all this term on the right hand side is going to get zeroed out. So that's y minus e over 2, and that's equal to 0, y equal to e over 2. And in fact, well, this is only a horizontal line, right? It's not going to be a diagonal line. We don't have any x's here. So, yes.
So, where'd you get the e over 2?
The e over 2, oh yes, from evaluating, because we were given the function and we want the slope at x equals 1. Well, to get the equation of the line, we plug in the value of x in the function to get the value of y. In some cases, the problem is going to come nicer, like find the equation of the tangent line to the curve, crazy function add, and they're going to give you actually an order pair. But in some cases, they just give you the value of x. We need to get the y value on our own to come up with whatever point is related to that value of x. Let's see if there's anything else over here. Another very classical problem. Well, I remember when I was a TA for this class a few years ago, we had one question like this on the exam for sure. So I'm going to put a star over here because you might want to pay extra attention to this kind of problem. Well, so we have the graphs of f and g. Well, we don't know what those functions are, and in fact we don't care. We really don't care because we can get the values here, and well, you'll see. So we're going to define two functions. Function p, which is the product between f and g, and function q, which is the quotient between f and g, where f and g are continuous functions, and they're asking us to evaluate p prime of 2 and q prime of 7. Well, number one, let's do p of x, big F of x, times g, big G of x. If we take the derivative, well, we're going to use the product rule. That's f prime g plus g prime f. All right, in other words, that's the derivative of the first factor times the second plus the derivative of the second factor times the first one. And now in this case, we want to find the derivative p prime when x equals to 2. So p of 2 equals f prime of 2 g of 2 plus g prime of 2 times f of 2. Well, we're gonna get all this information from our graph. All right. So I guess we can get the g of 2 and the f of those are easy to obtain because all we have to do is go to the graph of g and what's the value of y when x equals to 2. So what's the y value? 2. Okay, so this is 2. And what's f of 2? 3. Are you guys following me here?
Yes.
So far so good? Okay. Now, what's f prime of 2? Well, ultimately, what kind of information does the derivative give us about the function? That's the first thing we need to keep in mind every time we're doing this type of problem. So what's the derivative ultimately? The slope. So in this case, they're asking us for the slope for f when x equals to 2 and for the slope for the function g when x equals to 2. So let's go to each graph individually. So for the graph f, when x equals to 2, I'm going to go to the y value. But what's the slope over here? I mean, check this out because over here it's flat. We really have a horizontal tangent. And what's the slope of a horizontal tangent? 0. All right, 0. So 0. And what about the slope at x equals 2 on the function g? Well, the good thing, this is a linear function, and we can have a look at the ratio rise over run in this case, right? So like in this case, you could do rise 1, rise 2, rise 1, run 2, or even you could do rise 2, run 4, but it's the same as rising 1 and running 2, isn't it? So what would the slope be in that situation? So that's rise 1, run 2, 1 over 2. So let's put this into numbers. So that's a 0 times 2 plus 1/2 times 3. Well, 0 times 2 is just 0. 3 times 1/2, 3/2. All right. How about we have a look at a very similar question, but in this case dealing with quotient in this case. So q of x equals big F evaluated at x over big G of x. So we need to find the derivative of the quotient of this quotient function. So q prime, that's going to be, recall that this goes in order, f prime g minus g prime f. All right, the whole thing divided by the denominator g quantity squared. All right, so this is the quotient rule in action. We don't know what f of g, what f and g are, but we don't care because we know their graphs. We're going to get the same information from the graphs in a similar way that we did for p, but this time we want to get the slope or the derivative at 7. So forget about the number 2 as we did in the previous part. So let's go for x equals to 7. So that's 1, 2, 3, 4, 5, 6, 7. So 7 is here. So number 1, let's do the g's and the f, and then we do the derivatives afterwards. So let's get g of, oh wait a minute, let me label them with the numbers first. So f prime at 7, g of 7 minus g prime at 7 times f of f at 7. The whole thing divided by g evaluated at 7 quantity squared. So let me leave some room for labeling. Well, so let's find out first of all what's g of 7. Well, when f for the function g, the graph in blue, when x equals 7, what's the y value? 1. For the function f at 7, when x equals 7, what's the y value? Is that 1, 2, 3, 4, 5? 5. Now, for the derivatives, we're looking at the slope. So what's the slope on the function f, the one in red, when x equals to 7? Oh, okay, so this one might be a little bit tricky because, well, so we want to know the slope at x equals to 7 at this point, right? We want to know the slope at this point. But do we agree that the slope at that point is the same as the slope at this point? This point?
Did you just say it's 1/4?
Yes, so what I'm trying to say, I'm trying to find a way in which I can do a really nice run and a really nice run. So, rise 1, run how many? 4. Alright, so that's 1/4. And what about the derivative at 7 for the function g? Well, in this case we need to dive to and run 3, that is negative 3 and negative 2 and 3. So negative 2/3. Alright, I didn't forget about the function g because we already did it here. That's just 1. So putting the numbers together, q prime evaluated at 7, that's a 1/4 times 1 minus 2/3 minus negative 2/3 times 5. The whole thing divided by 1 squared. And this will be 1/4. Negative, negative, isn't it that positive? And that's at 10 over 3 over 1. But do we really that over 1? Not really. So 1/4 plus 10/3, and we need to combine these fractions together by finding LCDs. So the LCD in this case will be 12, and 1 times 3, which is 3, plus 10 times 4, which is 40, so 43 over 12. And that's final answer. Again, classical exam problem, and I really mean it. I was a TA for this class for 6 semesters, and in fact I graded this problem a few times, so I know for sure at least 90% of the times we assigned this second exam, a problem like this was there on the exam. All right, so let's see. So actually this is the end of section 3.2. Okay, let's go to section 3.3, another section that's finding derivatives of trigonometric function. Well, before we can even find derivatives of trigonometric functions, we need to first look at some limits involving trigonometric functions, and then look at some special limits that we will need in order to derive a formula for the derivative of both. And yes, we're going to go back one more time to the limits definition to find the derivative, but we need some sense of special limits first. So number 1, so let's evaluate each limit. So limit of cosine x over sine x minus 3 as x approaches 3. So again, first thing we want to do every time we have a limit problem is try to do the direct substitution. Hopefully we get a nice result. That's our final answer. But if we get something weird like 0 over 0, well, then we have to do some algebra to simplify the expression, get rid of that quotient that causes the 0 over 0 or negative infinity over infinity or plus minus quotient, well, and then we can compute the limit. Let's see if we're lucky enough for this one. Okay, so cosine 0 over sine 0 minus 3. So that's 1 over 0 minus 3. This is really nice. Negative 1/3. Alright?
But shouldn't you write it in like the parentheses too, so when you put the 3 comma for like the whatever it is?
Oh, not in this case because we're not evaluating a function. We are finding the limit. If we were given f of x equals cosine x over sine x minus 3, then in this case evaluating a function is the order pair. So evaluating a function is to determine whether we can step at that point in the graph. But limit is how close or where we're approaching as we have where are we getting as we approach x very, very closely. All right? Okay, limit of tangent theta as theta approaches pi over 2. All right. Well, maybe tangent pi over 2 might not be like very straightforward. So tangent pi over 2 might not be one of those easy values to determine just from the top of our head. However, my advice is to use trigonometric functions, and we know that the tangent function is the same as the quotient between sine over cosine. And well, what's sine of pi over 2? What's cosine of pi over 2? Well, we have a number over 0. When we have a number over 0, then we need to either make a table. I don't want to do a table. That's crazy. Especially for this kind of trigonometric values, we will have to deal with a lot of decimals, and you don't want to do that. So in this case, I will have to go through a graphic approach. All right. So in this case, how about we go about the graph of tangent? So in this case, it's going to look like this, with vertical asymptotes, negative pi over 2, pi over 2. All right. Well, so number one in this case, we want to evaluate the limit tangent theta as theta approaches plain vanilla theta pi over 2, not from the left, not from the right. Nevertheless, in this case, we have to look at this limit in both directions, from the left and from the right. So limit tangent theta as theta approaches pi over 2 from the left, limit theta approaching pi over 2 from the right. For the function tangent theta, well, let's look at these limits individually. So number one, so we want to approach pi over 2, which is this vertical asymptote. So we cannot get exactly to pi over 2 because, well, the function goes undefined. But we're using the limit notion to determine which y value are we apparently hitting, in this case by means of limit. So what happens when we approach this asymptote from the left? Where is this limit going to? Positive infinity. Now what about from the right? Where is this going to? Negative infinity. So this is the part where we need to compare whether these two limits agree or disagree. Are they the same limit from either side? That means plain vanilla pi over 2 does not exist. D and E. Alright? Okay guys, so for this couple of special limits and some computations with them, we're gonna do that next time.